All right, video number 4. We're going to talk about a few different things in this video. Some of the things I know have heard of before and have done many, many years ago. So we're going to kind of go through those pretty quickly. And when we get to very, very new stuff that I know you've never seen before, we'll really slow down and we will discuss it more in depth. So the mean, we said that is like our average. It is our arithmetic average. You guys know how to find the average. You add up all the things in your data set, you divide by how many things there are, and voila. I had mentioned this before in a previous video, but the symbol we're going to use for the mean will be x bar, and that's how you pronounce it, literally, x bar. It doesn't always have to be an x. It could be y bar, could be z bar, really whatever variable you want to use to represent your data, if you want to represent your data by a variable at all. But typically it's x bar. Then we have another measure of center, the median, which as you know is the middle value. And the most important thing for finding the median is all of your numbers, all your observations already have to be from smallest to biggest to be able to find the middle one technically. And then you would probably also remember that if you have an odd set of values, that the median is the true middle one. But if there is a even number of observations, then you have to find the average or the mean of the tie between the two middle ones. And that's all I'm really going to discuss about mean and median. So again, here's an example. You can look, here's a set of data of 20 numbers. The mean, you add up all these numbers, divide by 20, there's the mean. Here is a stem plot of our data. You can see that it is skewed right because the tail is down here towards the right. If you kind of tilt your head to the right, the smaller numbers being on the left, the larger numbers on the right. That there is a tie between 20 and 25, so we take the average, the mean of 20 and 25, and we get 22 and a half. Again, the symbol for median is just a capital M. There's nothing special about that. So another little example we'll actually kind of walk through here. You get a part-time job working at a restaurant. When you were interviewing for the position, the manager told you that the average wage earned by employees at the restaurant is 20 bucks an hour. You took the job without hesitation. When you got your first paycheck, you realized you were only being paid minimum wage. Outraged, you began to ask your coworkers what they make and found out they all make minimum wage. There are four employees other than your boss. How much does your boss have to make per hour to have told the truth about the average mean hourly wage? Assume minimum wage is $5.50 an hour. All right, so how we would set this up here, just think about this. You know what four people make. You've got four people making $5.50 each, plus you've got your boss and you don't know how much he makes. But if you were to divide all of that money by the 5 people working at the restaurant, the 4 employees and the boss, that average should come out to be what the boss originally told you of, $20. Okay? Now, the math for this is algebra 1 stuff here. You can multiply both sides by 5 to get rid of this divide by 5, which makes that now 100. And then 4 times 550 is $22. Subtract it over, and X would have to be $78 an hour. That's how much your boss makes, unfortunately. And you're getting screwed. Now, this all relates to an idea called non-resistant or resistant. The definition of non-resistant means that it is affected by outliers. It's not able to resist an outlier. Now, if you think about this set of data, you've got 4 people making $5.50 an hour and your boss making $78 an hour. Your boss is way far away from the 4 employees making $5.50. So your boss would be an outlier. And notice the mean, which is $20 here, doesn't really reflect the true average, if you will, of what people really make at the restaurant. You got 4 people making $5.50 and the boss making $78. 20 bucks is kind of a stretch, right? You felt like you were duped because the boss said $20 average. Now, the mean is not the only way to describe the center of the distribution. Another natural idea is to use the middle value, the median. So what is the median wage earned by employees at this restaurant? Well, if we lined up all of our dollar amounts of people's wages, we said we have 4 people making $5.50, and we found out our boss makes $78. So if we knock off beginning and last and the second last, there's our middle value. So the median is $5.50, okay, which would be a much more natural average to tell employees what they make. On average, the median amount of money is 5.50 an hour. Or if you'd said, hey, the mean amount of money is 20 bucks an hour, you're telling the truth more so with the 5.50 an hour versus the $20 an hour. Okay. Now, what if we exclude the boss's salary? What if we got rid of that $78? How does that affect the mean? Well, now we've got 4 employees all making 5.50 each. So if I added up all 4 of these numbers and divided by 4, well, if you think about this, 4 times 5.50 divided by 4 people, that's just going to cancel, and that will be the mean, is 5.50. So now the mean is decreased significantly. It brings the mean to be exactly the median. Will that always be true, that once you get rid of an outlier, that the mean and median will be the same? No, it just happened to work out in this case because all of our other values, once we got rid of the outlier, were all the same numbers here, these 550s. How does that affect the median? Well, let's see. We no longer truly have a middle number, right? So we would have to take the average of 550 and 550, which is 550. So it stays exactly the same. Will that always be true, that the median will stay the same once you get rid of an outlier? No. But if it does change, as I note here, it may change, but not nearly as much as the mean will change. Okay, the mean will have dramatic increase or decrease depending on where that outlier is at. So what did it mean to be resistant? It is a statistic that is, or a statistic that is resistant, is not affected by outliers. Okay, so would we say that the mean or the median is resistant to outliers? It's not affected. Well, we found out the median, in this case, wasn't affected at all by the outlier. But again, I said that it could be affected, but not as much as the mean. So the median is definitely more resistant to extreme values or outliers. Now, one thing I want to show you here that kind of leads us up into the next part is this little applet here. Now, I'm going to start putting some points out here. And so you see this yellow arrow? That just means that the mean and the median are the same value. Okay? And if you see green, and then there's a red one right behind it, the green represents the mean, and the red arrow represents the median. So let's say I have this little distribution here. Okay? It looks maybe approximately normal or symmetric. But watch what happens when I start throwing in some outliers. So I'm going to put some values way down here. Look at that green arrow, the mean. It's starting to chase all these outliers. But if you notice, the red arrow barely even budged. It's going to start budging more with the more values I put down here. Okay, but notice that green mean arrow starts taking off towards those outliers. It can't resist them. Okay, that's why the mean is non-resistant. But the median is resistant. It can resist all these extreme values down here much more so than the mean can. So that's what I wanted to show you there. So that kind of leads us into this next idea. And I mentioned this in a video earlier, that if you knew the mean and the median of a set of data, just using those two numbers, you can pretty much get a good idea for what shape the distribution is. So when the distribution is skewed to the left, remember that means our tail is on the left, then the mean, if you think about it, here's more of our extreme values down here in the tail. So the mean, our x bar, is going to start chasing those values. It's going to start moving to the left in this case. And the median is going to stick behind. It's not going to move as much. So the mean in this case is going to be less than the median. Okay, again, those extreme values. Now, those may not necessarily be outliers, but they're definitely extreme values way out there. All right, if the distribution is symmetric, okay, now the mean and median are probably going to be somewhere in this ballpark. Okay, the mean, median. If it's truly symmetric, exactly symmetric, then the mean and median will be exactly the same as each other. Okay, and if we have skewed right, then we're going to have more extreme values down this way, which means our mean is going to start sliding more that way. The median is going to stay behind. So in this case, the mean is going to be greater than the median. So the mean is always pulled towards what I wanted you to think about here is, what did we call this part of our distributions for skewed left and skewed right? We called those the tails of the distributions, okay, towards the extreme values, more the outliers. So if you are to describe a set of data by center, Which one do you choose? Do you pick mean or median? Well, in this case, if you have a symmetric distribution or approximately normal, you probably want to use mean. Okay? Mean is going to be the best option there. You can use median, but when we get into normal distributions, mean will definitely trump median. So if anything looks approximately normal, symmetric, anything kind of bell shape-ish, you probably want to stick with mean. But median does work. It does work okay. Now, if you have more of a skewed left or skewed right, we just said that means get pulled too far away from really the true center of the distribution. So if you have a skewed left or right distribution, you're definitely going to want to stick more with the median, more so than the mean. Now, I mentioned this in a few videos ago about the interquartile range. It's a type of spread. We talked about range being max minus min. Well, the interquartile range, it's not really the max minus min, but it's kind of like if you took the middle half of the data, and you took the max of the middle half, which is at the 75th percentile, and the lower end of the middle half, which is the 25th percentile, and subtracted those. So we're going to have to find values called the first quartile, Q1, and the third quartile, Q3. And the interquartile range is just the difference of Q3 minus Q1. Now, to find Q1 and Q3, in the next video we're going to talk about just doing this in your calculator essentially. Okay, but I just want to give you just a brief little rundown here of what it really means to be Q1 and Q3, the first and third quartile. Okay, you've got a set of data essentially where this goes from like the 0th percentile all the way up to here we've included all of our values, the 100th percentile. The median, the middle number, is essentially the 50th percentile. You can kind of think of it as Q2 if you like. Okay. Now, the first quartile is the 25th percentile. It means 25% of all the values have come before that Q1 value. Now, here's what I like to think of. Here is the first half of our data up to our median. Q1, the first quartile, is really the median of the first half of the data, right? Here's 50% of our data, and Q1 is the median of the first half. Likewise, Q3, if I go to the median here, Q3 is the median of the second half of the data. Okay, so if you took your second half of your data and you go, all right, well, what number's in the middle of my second half? Well, I got a tie. I got to find the average of 40 and 45. It's 42 and a half. There's Q3. Again, the calculators are going to find those values for us so that it makes it nice, quick, and simple. Now, the interquartile range, again, was the difference between Q3 and Q1. So Q3 is 42 and a half, Q1 is 15. We have an interquartile range of 27 and a half minutes. Okay. Now, you might think of, well, why would I want to use IQR more so than the range? Well, what if this number here was an outlier? What if your minimum value was an outlier? Then your spread is really deceiving to your audience. If you use the interquartile range, you're definitely going to be knocking out some potential outliers and saying, well, the middle 50% of my data has a spread of this much. And that's where really most of your data is going to lie, is usually around the middle 50%. So it's a much more accurate indicator of spread. All right, the last thing I want to talk about, and this is where I kind of want to slow down a little bit, and we will definitely practice more of this tomorrow in class together. And it is identifying outliers mathematically. Okay, here we have a rule for identifying if a value or values, could be multiple, are really outliers. And sometimes you may not have outliers, and sometimes you may have one, and sometimes you may have four. It really depends on your data. So the rule is we need to calculate the interquartile range, which we just talked about, and we're going to take that number and multiply it by 1.5. Now you might ask, why 1.5? Why 1.5 IQRs? Honestly, some guy a long time ago that kind of created this said, you know what, 1.5 interquartile range, that number, it's far enough away that if anything goes beyond it, it's probably an outlier. It was just some guy's best guess, and we've kind of stuck with it. Okay, so there's nothing really truly mathematically theoretical about this 1.5. It's just what someone thought was a good idea. Okay, and that's the honest truth about it. So here's how this 1.5 IQR rule for outliers works. So here was our IQR from before, from that last example we just looked at, the 27.5 minutes. So if you take 1.5 times that 27.5, here is how much we get to wiggle away from the first and third quartile. We get to wiggle around 41.25 minutes. Now here's the thing. Here's the main idea down here. You take the first quartile and subtract that number, that 41.25. So here we've got 15 minus that 41.25 gives us negative 26.25. So any value less than negative 26.25 is an outlier. Did we have any numbers that were less than negative 26.25 minutes? No, our smallest one here was 5. So there are no outliers on the, what we'd call the left end, the left tail of the distribution. There's no outliers there, okay? Now, if we go to the other end and say, now we start at Q3, the third quartile, which was 42.5. We said, all right, let's now add 1.5 IQRs above it. So we add that 41.25. So this 83.75 is kind of like a boundary. So we're saying any value more than 83.75 is an outlier. Did we have any values that were more than 83.75? We did. We had 85, which was it's beyond our limit here of 83.75. So now we can mathematically call this value an outlier. So we will definitely practice more tomorrow on being able to use this rule and making sure you guys fully understand it. Okay? So again, just to recap real quick before we end this, it's Q1, the first quartile, and this is where a lot of people get messed up. You subtract away from the first quartile, but you add to the third quartile. Okay, so if you've got your set of data here, here's Q1, you're going to subtract away 1.5 IQRs down to create a fence, which we said the fence was back in the negative territory, and then we want to take Q3 and add 1.5 IQRs above it, and boom, there was that fence, and here we had our outlier, our 85. So we're saying all of these numbers that are in here are okay. They're not outliers, but we do happen to have an outlier up here. Okay. Again, there could be times where you don't have outliers at all, and that's okay. That's kind of what we want to see, really. And that's it for video 4. We will practice more in class tomorrow. Adios and goodbye.